So today we will study applications of 3D computer vision and computer graphics. So let's first clarify what are computer vision and computer graphics, especially 3D computer vision and computer graphics. And then proceed to some applications like reconstruction, animation, and real lighting. So this slide from lecture 1, maybe some of you guys can remember this slide. So this shows the relationship between computer vision and computer graphics. So the goal of computer vision is reconstructing 3D scene from images, as this one shows. We have some images, capture the image with camera, and then we reconstruct some 3D scene using computer vision, and then the role of computer graphics is the opposite direction. Given 3D scene, we like to render images in screen space. That is the role of computer graphics. And 2D image is represented with pixel metrics, right? Just a square shape pixel metrics, like a 3-channel RGB metrics, RGB. And 3D scene, now we are familiar with some of this word, right? Object or geometry, shape. We have not material, but motion, 3D. So 3D scene could have any representation like point cloud, mesh, volume, implicit function, 3D Gaussians based on your preference. And so as I said, 3D computer vision, the role is to reconstruct 3D object or scene in camera and world coordinate system based on input image. And the goal of computer graphics is render 3D object scene to the screen space, the opposite direction. Roughly saying, very roughly saying, the role are kind of opposite. But people actually often want to control some things in 3D space, like control camera pose in 3D space. That is novel view synthesis, right? Based on reconstruct 3D scene, we maybe want to change camera pose, camera position, camera orientation, or intrinsic focal length. We'd like to change something. That gives us some images from new viewpoint, right? That is called novel view synthesis that we learn in NERF or 3D Gaussian splatting. Or we'd like to control light. Maybe we'd like to change the color of light, position of light. We'd like to control them. That is called relighting, changing light in 3D space, and control texture. So now the house is like a brown colored or some greenish grass, right? So maybe we can change the color of house to maybe red or blue colors. We can change texture in 3D space, or we can control pose. We can animate object. That is our final project, right? Maybe we can change the position of house. Maybe we can change rotation of house, scale of house. We can change them in 3D space. Or control scene, we can insert object in 3D scene. That is also final project, right? Maybe we can, we have new 3D Gaussian feature assets, and then we can just put them in the 3D scene. That is, so this kind of control in 3D is what people want. But why people want them in 3D space? Why not just do that in 2D space? We have images, right? We have images, and maybe we can just insert or change color or change light in image space. Why do we have to take care about 3D space? We have RGB images, right? RGB images. So let's say this is image. This is image. And then this is human. And maybe I insert another human here. Then I finish editing, inserting a new human in the image, right? And that's all. So why we need to take care about 3D control, 3D editing? In short word, view consistency. View consistency, primary reason why we need to take care about 3D when we control something or edit something. Let's say I insert this human, and then I slightly change viewpoint, then nothing is guaranteed that will produce good-looking images, right? So view consistency is maintaining geometrically consistent appearances across different viewpoints. So images rendered or generated from multiple views should align with a single underlying 3D structure, right? that is actually what is happening in our real world. We have this kind of single object, and then we change our viewpoint. But this object is a single object, right? I mean, if I look this direction, regardless of the viewpoint that I'm looking this object is a single object. It does not change, right? This kind of consistency is mathematically or naturally guaranteed in 3D space, so that we have view consistency when editing something in 3D space. So images rendered or generated from multiple views should align with a single underlying 3D structure, single underlying 3D structure. Ensure that object shape, identity, and pose remain stable when the camera position changes. And this shows the example. So imagine you want to edit something from images, like this example. I have some image, single image, and then I'd like to put something in this image, like adding some dog here. But you want edited image to provide consistent low value images. Like let's say I have video. This is time and height, width. For some certain frame, I edit something, but I want this modification to be included in all remaining frames. But if we just change a certain frame, then nothing gonna happen, right? Remaining frames, they have no idea how this modification happened. So we want this kind of control, edit, or modification to be included in all remaining frames. And in video, or in pixel space, that is actually not very easy. So you want the edited image to provide consistent low value images, like consistent edited video. 3D inherently or mathematically give you view consistency. That is the reason why conventionally people wanted to do some edit or control in 3D space. Mathematically, it gives us view consistency. But we will learn this later. 3D is not always the answer. It also has strength and weakness compared to image video generative models, especially these days, which we will learn later. But primary advantage of 3D implementation is view consistency. That is the very primary strength of 3D implementation. So as I introduced very briefly, we can do without 3D, right? Especially these days, we have very strong image video generative models, right? I mean, maybe we can give text prompt to change the color of this bird, or we can change the pose of this bird, right, based on text prompt. I think this example is too easy for these days, right? But this shows the typical failure case of image video generative models. So image video generative models, they do not rely on explicit 3D representation. So we just give text prompt, and then it just understand what it means, and then just produce corresponding pixels or images or videos, right? But they have strengths and weakness. I mean, but as you can see, I mean, if you simply change viewpoint, I mean, this bird should have the same appearance, right? But as you can see, the color of this head changes, right? Color changes. We can't see they are the same bird. So that means such kind of image video generative models lack view consistency. But this one also has strength and weakness compared to 3D implementation, which we'll learn later. But without 3D, maintaining this kind of view consistency is not trivial. Especially if you go to video level, not image level, video level, this kind of consistency is not very easy. But 3D, mathematically, naturally, it gives us view consistency. And that is the reason why people wanted to do something in 3D space. So, and the recovered 3D structure with 3D computer vision can be used in many cases, in addition to using it for computer graphics. So in previous slide, I introduced the output of 3D reconstruction. 3D computer vision can be used as an input of computer graphics, right? The image, CV, 3D scene, CG, right? The output of CV can be used as an input of computer graphics. That is one application of computer graphics, but it is not the only application. We have many applications, especially this kind of reconstruction or perception itself could be very important in robotics or autonomous driving. Robotics, we might not want to render some images, right? In robotics, we just want robots understand our word and understand my intention based on 3D perception, right? So robots need to understand what is happening in physical world, 3D or 4D space. And based on that perception, based on the understanding, robots can think how much torque it needs to apply, how much distance it needs to walk, how its hands are close to goal object. So this kind of 3D perception is necessary for robotics or autonomous driving. So CV is not, there can be many applications. One is the giving its output as the input of computer graphics. That is one role of computer vision, but it is not restricted to only one goal. We can use the reconstruction itself, like for example, robotics and autonomous driving, because they need to understand what is happening in physical world based on perceived or reconstructed 3D world. So to summary, computer vision, the goal is reconstruct 3D geometry, texture, camera. So recovering all these kind of components in 3D space from images. Input is image, output is some 3D stuff. And computer graphics, based on 3D stuff, we'd like to go back to image, just render images. And actually, in many cases, it's a little bit ambiguous to separate them. For example, nerve and 3D Gaussian splatting optimization. We learn both, right? When optimizing nerve for 3D Gaussian splatting, so the input is image, right? So it looks like input is image, and then we do something, we reconstruct some 3D geometry or 3D color, right? But we need to render them to optimize them, right? The primary loss function is render and compare, right? Render some image and then compare the rendered image with captured image. That is the primary loss function when optimizing nerve and 3D Gaussian splatting, right? So we need to recover nerve for 3D Gaussian splatting from images. That is it looks like computer vision, but they render images during the optimization because the primary loss function is image loss function. So it is, we go back to image, right? So it is computer graphics. So many problems actually are doing both. So it is not very kind of trivial to separate them perfectly. Actually, we do not have to separate them perfectly. So those are very related problems. Many problems are doing both together. And the representative examples are nerve and 3D Gaussian splatting optimization. So we recover something from images, and then we render them during optimization to optimize them, because the primary loss function is image loss. So there are two things already included in nerve and 3D Gaussian splatting, computer vision and computer graphics. So let's start with reconstruction. Reconstruction is image to 3D anything. Is primarily computer vision. Let me introduce 3D human pose estimation. This was my primary research topic when I was graduate student. But this kind of, what we learned from this 3D human pose estimation is not very specific to 3D human pose estimation. It can be applicable to any 3D reconstruction problems in computer vision. So the goal of human pose estimation is recover 3D human joint rotation from single image. Joint means we have like we have elbow or neck, hip, knee, ankle, wrist. We have such kind of joint, right, in our body. We have lots of joints. And the goal of human pose estimation is recovering 3D human joint rotations from single image. It gives us kinematic understanding of human motion, and is casual version of marker-based motion capture. So maybe you guys are familiar with this kind of picture, right? Typically, these days, AAA movie or video game, we have some marker-based motion capture studio. We have huge space, and we have many IR cameras, and then markers attached on actor's body, and then IR cameras track actor's motion, and then the track motion is used to animate virtual characters so that we can see this kind of rendered virtual characters based on humans' motion. But without this kind of expensive expert level setup, we can just use single image to track humans' motion, which can be very practical. I mean, we do not have to purchase lots of expensive gears. We do not have to hire expert level technicians or artists. We can just use single image, and then we can directly infer 3D human joint rotations. And that is a casual version of markup-based motion capture. So the, of course, dominant paradigm is using neural network. Neural network takes a single image and outputs 3D pose, shape, or camera parameters, some parameters. These days, architecture side is very saturated, highly converged to transformer. People just use transformer. You can see transformer, right? Transformer, and then just MLP. So architecture side, I don't think nothing's gonna happen just using transformer. But the challenge is data collection. How can we collect data to train this kind of neural network? That is always challenging. So to train this 3D pose estimation or any image to 3D reconstruction system, we need image and 3D pair, right? We need image and 3D pair data set. But we've learned that based on multiple geometry theory, we've learned that we can't get 3D data from a single image, right? We cannot get 3D data from a single image. We learned all this stuff, right? At least we need two views or multiple views. Of course, better. We need multiple viewpoints to get 3D data, right? Based on multiple geometry theory that we learned so far. So that people construct this kind of multi-view studio. Lots of cameras, calibrated, synchronized, 100 cameras, and then we hire actors, and then we capture data. We give script, and the actors do performance, and then we capture such kind of performance. And then we do 3D motion tracking, 3D reconstruction, all this stuff based on multi-view observations. That is typical way of capturing data, 3D data. Theoretically, it is good, right? But in practice, actually, it is not. Image appearances, color, light, such kind of thing of images from such capture studio are actually not very close to real world ones, right? Imagine you take images from this studio. Background is always bluish color. Background always have some cameras. But, in real world, we often go to many places, like these kind of places. We have friends, we have lots of object, light, we have lots of diverse light color, position. All this kind of variance cannot be included in this kind of multi-view setup, right? So that some system that's trained only on these images will not generalize to some in-the-world images. So let's say we have this kind of system, and then the input image is always from this studio. Bluish background, lots of cameras in the background. We always use such kind of images as input, and then we supervise the output of the network with the. We have good quality of 3D data, right? Because we have lots of cameras. Then we can supervise output of this network with the captured 3D data. Of course, we can train it. But the problem is that in test time, we want our system to work well on this kind of in-the-world images. Images from swimming pool, images from concert hall, images from outdoor. Our system, we always expect our system generalizable to any cases, right? But if you use only images from only this environment, then such kind of system might not generalize to this kind of in-the-world environment, unseen environment. There can be many diverse appearance of images, right? So that is problem. Of course, we can come up with some simple background replacement. We can make mask of foreground, and then we can simply randomly replace background. But that does not work. That does not work because light consistency. If we simply change the background, then the light of foreground, the light of background is very different. So it is, at first glance, we human can know such kind of image is synthetic image, not real one. So that data collection is very challenging. And this problem is applicable to any image to 3D reconstruction problems. In theory, we need multi-view setup to get 3D data, but images captured from such kind of environment has too restricted image appearances so that it might not generalize to in the wild images. That is the problem. That is challenge. So that people use a combination of multiple types of data sets. So the left one is multiple studio image, as I introduced. We have some studio, we have some constructed studio, we have many cameras, calibrated synchronized cameras, and then we can secure good quality of 3D annotation, but limitation is that restricted appearance. Background is always the same, light is always the same. Of course, we can construct many lights, but it cannot cover all the diversity of real-world lights and background combinations. And so that, the good point is that it has accurate 3D annotation, but the limitation is that it has restricted appearances. And synthetic image is the another type, like Unreal Engine. Unreal Engine is kind of physics engine that we can use to develop some video games. So we can use synthetic data set. Synthetic means in physics engine, we can import some environment, we can import some human, and then we can import light, and then we can render images from diverse viewpoint, that we can, as they are actually based on predefined 3D annotations, the 3D annotation is good, but image quality based on physics engine. But even these days, Unreal Engine 5, image appearance is a little bit unrealistic, like a 3D-ish image appearance quality, not very photorealistic. But it's much better than multiple studio image, but still a little bit far from realistic image appearances. In the wild image means images captured in daily life. We take lots of pictures in our daily life with our mobile phone, right? It has accurate 2D annotation. We learned that we cannot get 3D data from single image based on multiple geometry theory, right? So that we only have accurate 2D annotation, but image appearance is realistic, motions realistic. Interaction with object, interaction with human, all this kind of realistic. But data, we cannot get 3D data. So each data set type has strengths and weakness. Multiple Studio, let me briefly recap. Multiple Studio, we construct a expensive studio with many cameras, calibrated, synchronized, and then we can hire actors, and then we can give a script, and then we can capture their performance. Based on the multi-view cameras observations, we can get accurate 3D annotation, but the problem is that, as I said, image appearance is restricted. Background color, light, all the things are restricted. That is the limitation of multiple studio dataset. Synthetic dataset, like Unreal Engine, that just simply import predefined 3D assets, right? So that it has good annotation quality, 3D annotation is good, but image appearance is a little bit more diverse than this one because we can import many environments. We can import swimming pool environment, we can import outdoor environment, we can import many environments. But image appearance is a little bit unrealistic. And in the data set, YouTube videos or images on social media, we can use them. But we learn that from such kind of casually captured images, we cannot get 3D data based on multiple geometry theory. So that we only have 2D annotation, no 3D annotation, but image appearance is realistic, diverse, motion, realistic, diverse, interaction with object, human, realistic, diverse. So each data set type has strengths and weakness. So that people use combination of multiple types of data set. They construct a huge data set consists of multiple studio image, synthetic image, in-the-wild image. They use all of these kinds of data set types to train this kind of image to 3D reconstruction neural network. As I said, such challenge is applicable to all image to 3D reconstruction problems. I introduced only 3D human pose estimation, but then this kind of challenge is applicable to any image to 3D reconstruction problems. Image to 3D object reconstruction, image to 3D scene reconstruction, image to 3D human surface reconstruction. All this kind of image to 3D stuff are suffering from this kind of data set collection challenge. But these days, the power of synthetic data set is getting very powerful these days because the physics engine becomes very good these days. So when I was a student, synthetic image quality was very low. It was very bad, quality was very bad. So people at that time did not use synthetic data much. But these days, this kind of physics engine becomes much better than when I was a student. So people, some works purely use synthetic data without any in-the-wild image, without any multi-view studio images. And so such challenge is applicable to any image to 3D reconstruction problems. And on the other hand, we can secure a huge amount of image to the label pair data without many ambiguities, right? For example, let's say we have image, and then we want to label where human it is, human bounding box. We can, if we have infinite amount of money and time, then we can get infinite amount of data, right? Human object detection or segmentation. We can just draw some foreground pixels, right? If we have, this kind of 3D data, although we have infinite amount of money and time, we cannot get 3D data from this image. Because multi-view geometry theory tells us that we cannot get 3D data from single image. Although we have infinite amount of time and money, we cannot. But this kind of 2D stuff, like object detection, segmentation, or there are many 2D stuff, right? If we have infinite amount of time and money, we can secure huge amount of data set. Such kind of data set can be used to train your network. That is the reason why image to 2D tests are quite saturated these days. Object detection, segmentation. There are many image to 2D tests. Well, of course, some of them are still challenging, but very saturated, I think. Especially these days, many industry companies are collecting their own data set, and they have lots of money and time, right? They have lots of money and lots of human resource, so that they can secure huge amount of data set, so that image to 2D tests are quite saturated these days. But the 3D still data collection, in theory, multi-view geometry tells us that we cannot get 3D data from in-the-wild environment, so that it is not very trivial to secure good quality of data set. Of course, as I said, these days synthetic image becomes very good because of advancement of physics engine. Another application is 3D scene reconstruction from multiple images. It outputs 3D scene. This is called VGGT introduced in this year's CVPR. Based on, these are just multiple images. This can be images from video or multi-view images. It reconstructs 3D scene and camera parameter as well, and image matching. As you can see here, it takes images, multiple images, and there is some transformer inside of the network, and then outputs camera, depth map, point, and image matching. It looks like very familiar, right? We already learned this. Structure from motion and multi-view stereo. Structure from motion, multi-view stereo, right? This point map looks very dense, right? So it is not sparse point cloud. So, and it only takes input images. It outputs camera parameter and image matching as well. So this network is doing image matching, structure from motion, multi-view stereo at once using a single neural network. That is the value of this work. It takes only images. It does not recover any camera parameter, just the images. And then there's a trained transformer-based huge neural network. Outputs camera, depth map, point cloud, and then image matching, so that it includes what we learned so far, all the things. Image matching, structure from motion, multi-view stereo, all the things this network is doing this at once, just using a single network. The architecture, as I said, it's not very complicated, I think, just a transformer. Model works quite well and robust. And this shows the output of this network. So it looks like multi-view stereo only from few images without camera parameter, right? Yes, originally MVS, it requires camera parameters, but and sparse point cloud. But it looks like MVS, but with only a few images without camera parameter. And another difference is it is feed-forward neural network. Feed-forward means, so structure from motion or multi-view stereo, we optimize such representation for each scene, right? We learn, the structure from motion, for example, we initialize camera parameter based on initial two views, and then we gradually add an additional viewpoint, and then we keep optimize them by minimizing energy loss function. So it takes a little bit of time, like a few minutes maybe, but this kind of feed-forward network simply outputs all this stuff, image matching, camera, point, depth map, all the things together, less than 0.1 second. Very fast. We do not need to care about complicated optimization, just giving all the images, and then it can reconstruct all the things that we need based on multi-view images or single multi-view images. So very fast, and it is trained on huge amount of data set, so it is very robust, generalizable to many images from diverse environments. And as you can see, if we add more images, then we can reconstruct more regions. And as you can see, here, image looks very different. As you can see, image looks very different. Although image looks very different, it automatically finds some matched point across different viewpoint and then reconstruct a 3D single scene using your network in a feed-forward manner. Sorry. And robotics. As I introduced, we can use 3D computer vision for robotics. And this paper is introduced in this year's CORL. So we need to teach robots how to behave in new environment, and then we need to collect data. How can we collect data? There can be many approaches. This robotics community, it is not very converged. So there are many attempts to collect data. One of those approaches is using 3D perception, 3D reconstruction. We have a camera, and then humans do something like a walk on the street, and then we capture, and then we reconstruct all the human motion and 3D scene, and then based on this reconstructed human motion and 3D scene, we can supervise robots how to behave in this environment. In this stair, you need to walk upside, or in some environment you need to do something based on reconstructed human and 3D scene, right? So that we can use this kind of 3D reconstruction to obtain robot training data. And let's go to, now we are trying to do a combination of computer vision and computer graphics. And let me introduce my paper published in last year, ECCB. The goal is, this is not, this paper, this animation stuff, it can be used in not only human, but also like object or animal or scene, any cases. And the goal is to, from monocular video, like a single person, we'd like to animate this human into arbitrary poses. So they reconstruct some canonical representation and then animate to screen space. So this is computer vision. From this sparse view images, we reconstruct some canonical representation, and then based on reconstruct canonical representation, we render images based on canonical representation. So that is computer graphics. So it's a combination of computer vision and computer graphics. And so data collection is always challenging. So we only require a few limited training frames that only needs limited body pose, limited hand pose, limited facial expression. How can we generalize it to novel pose and facial expression? So this work uses combination of 3D Gaussian splatting and surface mesh. Surface mesh, we have triangle, right? Triangle means we have connectivity between vertices. This vertex and this vertex is connected. This vertex is connected. We have geometric prior, such kind of geometric prior. But surface mesh, it is not very easy to represent thin geometry like cloth and hair. 3D Gaussian, you can model cloth and hair better than surface mesh, but the connectivity is not defined. So that we combine them together to have 3D Gaussian with connectivity. So that this shows the effectiveness of the combination of 3D Gaussian splatting and surface mesh. As you can see, there are bumpy geometry and ugly texture, but here it's a smooth geometry and texture. And architecture is like you do not have to memorize this paper. You can just do what is happening, understand what is happening in this paper. So there are many. We haven't learned triangle plane. So we have learned MLP, right? So MLP outputs some Gaussian features like mean offset, scale offset, and color offset, and then we reconstruct some canonical representation, and then we animate it with input pose and render with input camera parameter, and then we can have animated representation of human.
Video. We create an animated.
Okay, and this is me captured. The left one is captured in from my apartment, and then the right one shows the video is from YouTube, and then use 3D pose estimation. We learned so far, right? Human pose estimation, and then animated with novel pose. And this is also shows our ongoing work, our lab's ongoing work. So try to represent cloth better. So that was the animation. So in our final project, we only use a very simple animation, just changing scale of object or moving some object, right? We do not take care about this kind of deformable object. For example, with human, maybe we want humans to animate only arm or some desired motion, but in final project, we haven't learned such kind of complicated animation. So we just simply do the global animation, globally changing size of object, globally changing position of object, or globally changing rotation of object. That's enough. Anyway, animation is what people often want to do in 3D space. Animate something in 3D space and then render to 2D space. And then real lighting is very computer graphic stuff. So the goal of real lighting is making 3D representation generalizable to new novel eliminations. So the left one shows that, if there's a point, if there's a point light source, although there's a light, there's nothing is happening. But in real world, if we have point light source, there should be some shadow and some shade, right? This is relighting is not activated. Here relighting is activated. This is also our work when I was in Meta, introduced in last year's CVPR. So we collect huge amounts of light stage data, and then we do hand tracking, and then do the model universal prior or relightable hand, and then as you can see, the illumination changes, but according to change in illumination, the texture of human skin changes. And let's go to skip some details. And this shows, so we built a combination of physical branch and neural branch. Physical branch is classical computer graphics. We use physical BRDF and get diffuse and specular reflection map to get physically based rendered images. And then we use neural network, another rendering engine. And here is the qualitative comparison. Yes. So there's an environment, background is environment, 360-degree environment map. And then we rotate the camera viewpoint. Then the hand skin changes color according to the environment and viewpoint, right? And this one is also about relighting. Yes. So we change the position of light or rotation of light. This is visualize normal map. As I introduced, normal is necessary for the relighting. And we change the light position and light orientation. And then according to the change, this one shows maybe specular reflection, specular rendering, or spherical Gaussians. And you put this representation to novel environment, the skin color changes. So in computer graphics community, people are aiming very high quality rendering, like this kind of there'll be natural hair and eyebrow. And this is captured with headset, VR headset. Yes, VR headset. So the quality is really good, very close to ground truth. Anyway, the goal of relighting is to changing light orientation and rotation, position, and we want the reconstruct 3D scene include such kind of changed light in the final rendering. That is the goal of relighting. Okay, and so today we studied applications, computer vision and computer graphics, like reconstruction, animation, relighting. There can be actually many things. I can't cover all the stuff. We can maybe insert new object. We can change texture. We can change style of 3D scene. We can do many things. And the reason why we are focusing on 3D control is that it gives us view consistency, as I said. If we change something in 3D space, and then regardless of which viewpoint we are taking, it gives us our desired images with our desired modification, right? That is the primary reason why we do such kind of control modification edit in 3D space. And next we will cover generative models. First we will cover basic understanding of generative models like PCA, VAE, GAN, diffusion. So why they are, the generative model is also not very new thing. It is started to be studied quite a long time ago. So what is the difference between discriminative approach and generative approach? And how can they be used for 3D? And these days achievement, do we still need 3D? That is also quite interesting question for generative models. So we will study generative models from next time. And any questions about application?